Hi, in this talk I'm going to go over my own speculations, and that's all they are, as far as gravity is concerned, because I think there are big problems there, and I'm not happy with the current proposals that we have on the table to deal with these problems. So for weak gravity, that's where it's 10 orders of magnitude smaller than it is here on Earth. And if we just do Newton's law out of the box, it has this Keplerian decline, which is inconsistent with what we've seen. So to me, the graph of a velocity of a spiral galaxy as you go out from the center, well, actually should be redrawn. It should be showing you the momentum profile, because velocity is not a conserved thing. Momentum is. Gravity is about changes in momentum. And this graph is missing a good portion of the data you need. It doesn't have the mass, okay? It should say the visible mass looks like this. And what this is an exponentially decaying function. So momentum is the product of that flat part with an exponentially decaying mass distribution, which means that it is an exponentially decaying function. And so the graph tells you what the answer is. It's saying as directly as a graph can, because I actually can't speak, that there is a stable velocity, constant velocity, exponentially decaying mass solution involving weak gravity. And so let's construct one. Let's do whatever the heck we have to do what the graph tells us directly. Okay, once we put on the mass there and say we're dealing with momentum and changes in momentum. Okay, so that's what I've tried a couple of times. The math for this thing is really actually quite difficult. Just for, you know, it took Alar Tomre, someone that bright, to deal with what are they calling, elliptical integrals, and I don't know how to do those. I've got a book where I've read through how it's done. It's genuinely scary kind of stuff, but I think maybe we have to use the product rule of calculus, because the product rule of calculus says constant mass times a change in velocity. Oh, that's the MA thing. That works for apples falling, but it's not relevant here because the velocity is not changing. So the other term is somehow a changing mass. Okay, they usually think about that as the rocket science term, but in this case it's the mass relative compared to where it is in the center. It keeps dropping off exponentially. That's what we have to explain. A constant velocity times this changing mass relative to the center of the galaxy. So that's where my money is, hoping for a constant velocity solution where, you know, the mass is changing all over the place. So then we think about old gravity, kind of the Big Bang. You go, well, one thing you need is a constant velocity solution. Oh, I just said that. Oh, and the mass has got to be changing everywhere, which is kind of what the Big Bang's all about. I mean, mass used to be like all here, and now it's like all over the place. So it suggests to me that maybe we might kill two birds with one stone. I don't know how to deal with the math of the Big Bang. I've looked for it, and so far I haven't been able to handle it. Okay, but it's sounding to me like this constant velocity solution involving gravity. Those are similar problems. Okay, maybe. Okay, that's my speculation. And then there's this big gravity issue. Okay, like the scale of the whole universe. All right. Well, if we go from one term to describe gravity, the familiar MA deals with an apple, to this other term that involves where things are. Gravity changes where things are, stuff is. Well, if you have these two terms, they might like do stuff with each other. They might change who should be the active player. I don't know. It's actually, here's another area. I don't know how to get to playing with their equations and stuff. But if we now have two terms that are important when gravity gets super weak, that might actually come into play into this kind of thing. I can't know, but it certainly guides my investigations. And then how about small gravity? Well, look, the brightest people on the planet have been trying to deal with this problem for like 80 years, and it hasn't worked out. It's like, well, why not? And I think that you can't get general relativity to work with quantum mechanics. I think that's a safe bet. Okay, so we need a new theory. Okay, and I'm thinking of a very small theory. Now, it's not the smallest theory. The smallest theory is what's called a scalar theory. And the problem with that is it says, you know, the stuff in space should get small, and the stuff in time should get small, like this. And if you think about that ratio will of space over changes in time, that ratio will never change, and therefore there will be no bending. And therefore, because we've seen plenty of bending of starlight around gravitational sources, it's thoroughly wrong. So mine's just a tiny step bigger than a formal scalar theory for gravity. And the tiny but absolutely essential step is it says, okay, you use this to describe how changes in space happen based on, you know, one mass there. Okay? And that for the changes in time, they're the inverse of those changes in space. So now when I look at the ratio of changes in space, let's say it's getting a little larger, to now changes in time, well, they're getting a little smaller, but we're doing the ratio, so it's kind of like that squared. It's going to change. We're going to get light bending. But the kinds of problems I face in such a proposal is I have to formalize why I am making the space part bigger while making the time part smaller in a way that, you know, somebody won't say you're just cheating. There's real questions about whether I can formalize that kind of idea and get people to think about what I'm doing is legal or not. But it certainly is. It certainly makes sense to me that if the one difference is how time is affected versus space, and the thing is that time and space, although they live in space-time, it's pretty clear we treat them differently now. Okay, we treat them differently because, you know, one of them gets a factor of c and the other one doesn't. Okay, and it's your choice where you put the c. You know, but you can't put them on both. You got to put one on one and one on the other. When you kind of square these up, okay, you're going to decide that either the time part is squared is positive, or the space part is positive, space part squared, and the other one is negative. So we already do this. And what I'm saying is when you're in a gravitational field and you can no longer use constants in front of your squared terms, you can't use a +1 and a -1. Okay, what I'm saying is when that becomes a dynamic quantity, the quantity that depends only on gravity, what I'm saying is for space, it'll make it larger. And for time, it'll do its inverse. It'll make it smaller. So that when we take the ratio, we can see that, you know, we're going to get light bending. And all I have to do is formalize that. Not easy for a fellow like myself to do, but it's certainly worthy of my time and effort. All right. Thank you very much.